Few people know, but there are huge problems in understanding the processes of star formation. What is the essence of these problems? How do data from the latest telescopes bring us closer to solving them? And why will this solution lead to a revolution in astrophysics and cosmology? The first problem concerns the formation of massive and bright stars. The problem is that we still do not know how bright, massive stars form. The point is that when a gas cloud condenses and begins to form a star, the first thermonuclear reactions are ignited, and the star begins to release a lot of energy in the form of radiation and particles, which is called stellar wind. And this stellar wind blows away all the nearby gas and prevents the star from further increasing its mass. The mass at which a star begins to burn is less than the mass of our Sun. The original theoretical mass limit for a newborn star was quite modest. But theorists, using all sorts of models and assumptions, have increased it. In addition, all kinds of accretion models have been proposed in which accretion can occur regardless of the stellar wind. As a result, the maximum theoretical mass limit reached tens of solar masses. But even despite all these very artificial conditions, we see stars that significantly exceed this limit. And this problem still remains unsolved. But that's not all. Observations of nearby hydrogen clouds in our galaxy show that only a small fraction of this gas turns into stars. This problem can be called star formation inefficiency or slow star formation. At the same time, we see in some galaxies much higher rates of star formation. In particular, in the spiral arms of galaxies, we see this incredibly high rate of star formation. And these two still unresolved problems seem to hint to us that there are some gaps in our understanding of this process. It appears that there is some other, unknown mechanism of star formation. What do the data from the newest telescopes that I mentioned at the beginning of the video say? A very distant galaxy with a very high rate of star formation has been discovered. But the region of star formation in this galaxy coincides with the location of the jet. Jet, radio jet, relativistic jet, or sometimes called astrophysical jet. These are all names for jets coming from the region of a supermassive black hole. Often, the matter in these jets moves at near light speed. Such objects with jets are called quasars or active galactic nuclei. Jets are also found in black holes of stellar mass, neutron stars, and other very dense objects. Calculations show that in this galaxy, at least 30% of these newborn stars were formed under the influence of the jet. And this is not the first such discovery. Other galaxies have been found in the early universe in which regions of high star formation coincide with the locations of jets. And this applies not only to distant galaxies. In the nearby universe, there are also observations of how the jet triggers star formation. And even in the jet of the Centaurus A galaxy, there are newly formed stars. And simulations confirm that the jet can enhance star formation. And every year there is more evidence like this, since highly sensitive equipment appeared. But more than that, this equipment made it possible to detect jets in many Seyfert galaxies. But the jets in these galaxies are very different from the usual jets. More precisely, not the jets themselves, but their direction. Seyfert galaxies are galaxies that also belong to galaxies with an active nucleus. Only instead of the usual jets, they have what in astrophysics is called radiolobes. These are lobe-shaped areas near the core that actively emit radio waves. Another characteristic feature of Seyfert galaxies is that the radiation from the nuclei of these galaxies has broad emission lines, which indicates high-speed gas movements. Initially, it was believed that this was the movement of gas in the accretion disk. But there are several arguments against this version, which I discussed in detail in video number 10. The nature of this radiation in Seyfert galaxies still remains a mystery. And in recent years, there have been a lot of reports that these Seyfert galaxies probably have a jet that's located inside the disk. But what is also important is that in one of these galaxies with a supposed jet in the disk, the radiation in the region of this supposed jet is similar to the radiation of Liner galaxies. Liner galaxies are another type of active nucleus galaxy, with emission similar to that of Seyfert galaxies, but with a number of differences. And the researchers associate this radiation with the impact of the jet on the stars and the interstellar medium of the disk. Therefore, there is reason to believe that in other galaxies, the Liner radiation is also caused by the presence of a jet in the disk. Now pay attention to an interesting fact. Both Seyfert galaxies and Liner galaxies are mostly spiral galaxies. A key feature of spiral galaxies is the presence of a spiral pattern in the disk. The spiral arms that make up this pattern are characterized by a high content of cold gas, high rates of star formation, and the main luminosity of these spiral arms is provided by bright, massive stars. In other words, the spiral arms are the region of the galaxy where star formation theory fails and cannot explain the observations. Now imagine a quasar with jets that for some reason rotates in the plane of the jets. What will it look like? Exactly. It will be a spiral. But here we need to take into account one important difference. In spiral galaxies, black holes are not very massive, so the energy of their jets is not very high. And according to indirect estimates, based on the speed of outflows, the speed of movement in them varies from tens of kilometers per second to several thousand kilometers per second. And if such not very fast movement of gas occurs in the disk, it will enhance star formation in the place where this movement occurs. And a little later I will describe what exactly might be happening there. The proportion of Seyfert galaxies, according to very old studies, is about 15% of all spiral galaxies. And Liner galaxies, according to the same very old estimates, make up about half of all spiral galaxies. And it turns out that the majority of spiral galaxies presumably have a jet directed into the disk. Add to this the fact that jets like the one you see on the screen are only observed in elliptical and lenticular galaxies. And in spiral galaxies they are almost never observed. And if they are observed, these jets are short-lived and very weak. And this is another unsolved mystery of astrophysics. And this assumption about jets in the disk comes from simple logic. If a galaxy is elliptical or lenticular, then it does not always, but it does have traditional astrophysical jets. And if the galaxy is spiral, then it does not have traditional jets, but there is mysterious radiation in Seyfert and Liner galaxies. And there are spiral arms in which the rate and efficiency of star formation are so high that star formation theory cannot explain them. And research in recent years suggests that this radiation in Seyfert and Liner galaxies may be due to a jet in the disk. Moreover, high-speed gas movements were discovered in the disks of Seyfert galaxies. And the majority of spiral galaxies are Seyfert and Liner galaxies. Therefore, it is logical to assume that all spiral galaxies have jets directed into the disk. However, not every spiral galaxy has signs of a jet's presence that break through the thickness of the disk. Let's get back to the problems of star formation. Apparently, the inefficiency of converting gas clouds into stars actually occurs. And clouds really aren't capable of forming stars efficiently. But how then do such high rates of star formation occur in spiral arms? It can be assumed that in spiral arms not all stars that look like newborns are such. Imagine the situation that a stream of gas moves through the disk. On its way it encounters an old star. And this old star gets a portion of gas. This gas, mixed with the gas of the star, significantly reduces the proportion of helium. Or this gas is distributed around the star like a shell of hydrogen and therefore the star becomes as if it were newborn. Moreover, this star, without any theoretical tricks, can very easily exceed the theoretical limit of the star's mass. Because its stellar wind is not at all an obstacle for the gas moving at high speed in the jet. The end result is massive, bright stars that break the theoretical mass limit. But this same mechanism also explains the second problem of star formation. The efficiency or rate of star formation is measured by the mass of the newborn stars. And the stars that only appear to be newborns had a certain mass before meeting the jet. Therefore, already at the stage of calculating the rate of star formation, an error occurs due to the fact that the mass of the old star is also taken into account. Moreover, if a star is in the path of a jet for a long time, it can increase its mass for a long time, and thus very efficiently convert the mass of gas from the jet into the mass of the star. As a result, when estimating the rate of star formation, the mass of the old star is mistakenly taken into account. But what really happens is that there is an extremely efficient conversion of gas mass into stellar mass. That is why we observe such incredible rates of star formation in spiral arms. But as you probably know, if a star receives a large portion of gas, then depending on the stage of evolution and the processes occurring in its depths, a nova or supernova explosion may occur in the form of a core collapse or a thermonuclear explosion of the entire star. And core collapse supernovae most often occur in spiral arms. And we'll talk about this in more detail in another video. And I have a surprise for you on this topic, which surprised me too, so don't miss it. But here one can object that the supernova explosion is a stage in the evolution of massive stars. And since most massive stars are in spiral arms, it is logical that core collapse supernovae occur in spiral arms. And jets have nothing to do with it. And this would be logical and fair if the mechanism for the formation of such massive stars and the reason for their location in spiral arms were known. But since we don't know either one, it is fair to assume that this is precisely a consequence of the presence of jets. I'm sure some of you would like to object that the spiral arms are density waves caused by the Lindblad resonance. And in general, gas moves from the edges of the disk to the center of the galaxy. Okay then, I'll tell you this. In simulations, it is very difficult to get a stable spiral structure, especially a barred spiral. Therefore, there is a problem called the problem of missing bars. In general, these two models are somewhat competitive with each other. According to the density wave theory, a certain resonance of the star's orbits is created in the galaxy's disk, which results in the formation of a spiral structure, in which, due to the gravity of the increased concentration of stars, the concentration of gas increases and therefore the rate of star formation increases. This is the main version, but it has some disadvantages. For example, over time the gas should run out and star formation will cease. Spiral arms of gas also exist in places where the density of matter is too low to create density waves. There is also a hypothesis that gas from the outside flows in the form of filaments into the disk of the galaxy. As it moves, new stars are formed, and the trajectory of its movement itself creates a kind of spiral. This influx of gas was also supposed to solve the angular momentum problem. The problem is that the simulations produce galaxies that are very different from those in reality. Once the gas reaches the center, it falls onto the galaxy's core and feeds a black hole, which in turn can eject some of this gas as a jet. Or some of the gas is ejected due to supernova explosions. This ejected gas then falls back onto the disk of the galaxy, thereby creating a galactic fountain, which is intended to solve another problem, the so-called G-dwarf paradox or G-dwarf problem. This is the problem of explaining a very strange fact, the almost identical metallicity of the disk stars, which was initially discovered on G-dwarfs. This paradox is very easily explained through a jet moving in a disk. This is also discussed in video number 10. But if you just watch this video carefully, then it won't be difficult for you to guess. Gas inflow from outside. What's wrong with this version? Despite years of attempts to detect these streams of inflowing gas, astronomers, on the contrary, observe gas outflows from spiral galaxies. Outflows in a biconical shape and outflows in the plane of the disk. And if earlier these assumptions about a jet in a disk were rare and sounded somehow cautious and uncertain, now such assumptions sound more bold, because their number is increasing. But it is important to understand that, in the understanding of researchers, these jets are almost all relativistic. That's why they are surprised by the spiral or S-shaped jet. In their understanding, the jet should be straight and motionless. Although there is already quite a lot of evidence of precession and rotation of jets. I know some of you are going to argue now. No, jets cannot rotate, because they are a consequence of the movement of gas in the accretion disk, as well as the magnetic field of the black hole. What's the logic here? The generally accepted mechanism for jet formation is the accretion disk model. The accretion disk rotates in a certain plane, and in order for the jet to smoothly change its direction, it is necessary for the accretion disk to smoothly change its plane of rotation. And this is impossible due to the conservation of angular momentum. The same applies to the black hole's magnetic field, which is associated with its rotation, and the poles of its magnetic field cannot change direction due to the same conservation of angular momentum. There are also other arguments against the accretion disk model, and you can learn about them from the same video number 10. But you can also use simple logic, which for some reason is not used in relation to the accretion disk. We see many different galaxies with jets, among which are almost always elliptical and lenticular. And if these jets really are a consequence of accretion in the accretion disk, then why does this accretion disk not work and create jets in spiral galaxies? Ask yourself this, those who think that gas flows down the spiral arms to the core, and in the area of the bar it falls onto the core. But as always, regardless of our understanding of phenomena, observations, logic and scientific methods will move our knowledge to a new level, and they will bring closer the moment when it will be impossible to ignore all these jets discovered in spiral galaxies, and it will become obvious that the spiral structure is not at all density waves or inflowing external gas. And when this becomes clear, the understanding will come that the evolution of galaxies does not occur as the dominant model suggests, but in a completely different way. And the answer to the question of where the matter in the jets comes from could completely turn the whole of cosmology upside down. In this context, the DESI or Dark Energy Spectroscopic Instrument Survey made very interesting discoveries. It turned out that the proportion of dwarf galaxies with active nuclei is 3 times greater than previously thought. And note that we are talking about active black holes of intermediate mass, the existence of which has been in question for many decades. But now they have begun to be discovered in dwarf galaxies. And in our galaxy, in the globular cluster Omega Centauri, there is presumably a medium-mass black hole. And it turns out that such black holes do not exist alone. They are surrounded by a large number of stars, and that's why they couldn't be found for a long time. But here a natural question arises. If all intermediate-mass black holes are surrounded by a large number of stars, which of them is primary? A black hole is being formed in a cluster of stars, or a black hole is forming this cluster of stars around itself. And even in the scientific community, the question arises, which came first, supermassive black holes or galaxies? The answer probably lies somewhere in the middle, because on average, the mass of galaxies is proportional to the mass of the black holes at their centers. And all this fits perfectly into the model of galaxy evolution, according to which a galaxy is formed under the influence of a black hole. Therefore, I can say with confidence that the revolution in astrophysics and cosmology is approaching very quickly.